damn it. Hi, Joe. How you doing? Hi, Joe.
Hello.
Hi. Did we get through all of the shapes?
What was the-
Octahedral?
I think we did, yeah.
I was pretty sure we did. I was more in tune with what we did in the evening class as opposed to what happened in the morning class. So, how you doing? Okay.
Yeah, I just got my part to make me have 2 monitors, so
You got your what?
I have 2 computer screens. So
Ah,
I was waiting for a part in the mail so I could have 2 screens. And it
is
just came
this
in
one
today,
where
so
you can flip? You can actually take the mouse and flip between them.
my mouse goes between both of them.
That's great. That's good. I've
Yes,
seen them
yeah.
work. I'm afraid that would just totally put me into a schizophrenic fall.
It's not bad. I've always wanted a good computer, so I've had a good computer for a couple months now, and then I just upgrade to a second monitor. So
Well, that's fantastic. That's great. You're going to need to use
I'm
it
happy.
are you going to need to use it in what you do?
Not really. I like to play video games, so it's good to have like a screen over here, and then I look at the other screen for other stuff.
I'm glad there's a serious purpose behind it.
Well, and you know, also school wise, like since it's online, I can put like work on left and work on the right, so
Uh-huh.
it's better with that. With alt
So
tabbing everything.
that sounds good. Sounds real good, Joe. Are you getting this stuff?
Yeah, I'm doing good. I mean, it's the loose structure ain't that hard for me, to be honest.
What about
I
Vesper?
understand. That's a little confusing, but I feel like once I get used to it,
All right,
I look
because
at
I'm
look
going to pile
problems.
on.
That's my only problem. Yeah.
I'm piling on today. Okay. We're going to get into definitely hybridization because that's the next thing we're having do. And then beyond that, we're going to be getting into molecular orbital theory, which something I don't really believe in, but it's something they make me teach. Okay, so Blake, Dylan, would you agree I got through all of the shapes on Tuesday?
Yeah.
Got through octahedron. That's where we ended it, right?
Yeah, I think we started right. We're going to start with polarity, I think.
Okay, I went through the larger molecules. That was the last thing I did, right?
Yeah.
The slide that's up there right now, I've already been through, right?
I think so, yeah.
Yeah,
But
'cause you made me do that.
let me just go through that just to reiterate. When you get a large molecule like this, you can't, nobody can ask you what the shape of that is. What they have to do is they have to ask you what the shape is around which center atom. Because this case, we have 3 center atoms. Each one of them has a different shape associated with it. The left carbon is tetrahedron. The middle carbon is trigonoplanar. And this oxygen has a bent shape to it. So you have to talk about each individual center atom by itself. All right, now, do you guys remember what causes a bond to be polar?
The placement of the electrons.
Kind of, sort of. What would make the electrons spend more time around one atom than another?
the electronegativity of the atom.
Electronegativity. If there's an electronegative difference, then the bond is going to be such that the electrons spend more time around one and a little time around the other. So because they spend much more time around the one, that side's going to be negative. The other side is going to be positive. Okay? Now, we can use that concept to define the polarity of the entire molecule. And polarity is nothing more than when we put a molecule in a magnetic field, if that molecule has an unequal distribution of charges, say one side's negative, the other side's positive. This side's positive, this side's negative. Well, if my magnetic field is such that this end's positive and this end's negative, when I have my molecule in that magnetic field, it's going to orient so that the negative side of the molecule is pointing towards the positive side of the magnetic field. Does this kind of make sense to everybody?
Yeah.
Yeah.
Well, what this helps determine is it's like you have segregated molecules now. You have those molecules that are polar and those molecules that are not polar. All right. Because they're segregated, the polar molecules want to be with the polar molecules, the nonpolars want to be with the nonpolars, and you can't get them to mix very easily. There are reasons for this, and we're going to get into them in the next chapter. But for right now, just know that polar molecules don't mix with nonpolar molecules. And we have a way of determining, of looking at those molecules and determining whether they're going to be polar or not. Polarity. Because of this, because polar wants to be associated with polar, this means we know that polar molecules want to be dissolved in polar solvents. And this also means that nonpolar want to be with nonpolar. So you also know that polar do not want to be with nonpolar. They kind of like separate out. That's polarity is what does this property. I've already mentioned that. This is stuff I've already mentioned. Okay. If I have a hydrogen fluoride bond, electrons are going to spend more time around fluorine than they are hydrogen. So the fluorine is going to be negatively charged. Now, back in medieval times, they had this quaint little custom called drawing and quartering. And basically what they would do is they would tie a person's limbs to 4 different horses and yell, "Giddy up." Now, if each horse moved with the same force, yeah, the limbs would get torn off, but is the torso going to move?
No.
Torso's not going to move. Think about it another way. If you have a 250-pound man pulling on a tug of rope this way, another 250-pound man pulling it this way, is the center of the rope going to move?
No.
So that has everything to do with the polarity of a molecule. If you have two forces pulling in equal and opposite directions, then you don't have a negative side, you don't have a positive side. You get everything just distributed the way it is. Think of it this way. If I had that molecule with negative points on both sides, and again, my magnetic field is positive here, negative here. When this one tries to move towards the positive, this one gets repelled by the negative. So it moves back here. So you put this molecule in a magnetic field, it doesn't move. Is that making sense to you?
Yeah.
So we have to, in order to have a polar bond, in order for the molecule to be polar, two situations have to be satisfied. The first is it needs polar bonds. Hi, David. The first thing that has to happen is the molecule has to have polar bonds. The second thing is that molecule has to be asymmetric. So what you got to do is you got to look at the Lewis dot structure you've drawn. From that, you have to turn it into the Vesper model to see how that particular molecule looks in space. If it is asymmetrical and if it has polar bonds, you have a polar molecule. If it doesn't have polar bonds, not a polar molecule. If the molecule is symmetrical, not a polar molecule. And to do this, you kind of have to understand about vectors. If I have a water molecule, yeah, I'm pulling up all the way with a negative force here. But I'm also pulling down with a positive force based upon the vector, which means that the vector gives me some contribution on the x-axis, some on the y-axis. So if we look at these, Joe, is HCl a polar bond? Joe, you out there?
So I was muted, yes.
No, okay. This HCl is over here. Does it have a polar bond?
It's going to HCl, so no.
Wait, remember, Cl is much more electronegative than hydrogen. So
It
is this
does.
bond polar?
Yes.
Bond is polar. It satisfies the first requirement. Is it symmetrical?
Yes.
I cut this down the center here, Joe. One side's
Oh,
an
no,
H.
no, yeah. No, it's bigger, yeah.
All right, so does it satisfy both criteria?
No.
You just said it's polar and you just said it's asymmetrical.
Oh, asymmetrical. I thought you said symmetrical.
No,
But
asymmetrical.
yes, then it does. It does then. It does.
I'm sorry. Sorry if you misunderstood me. HCl has a polar bond and it is asymmetrical. It satisfies everything.
Yeah, then we
HCl
sure,
is a polar molecule. All right, Blake, you out there, Blake?
Yes.
All right. We're looking at ammonia here. This is the top right molecule. Does it have polar bonds?
Yes.
Okay. Is it symmetrical?
Yes.
Blake, do you see 3 hydrogens on top of the nitrogen?
I mean, are you talking about splitting the hydrogen?
No, I'm trying to talk about the whole molecule. If you look at this whole molecule, the nitrogen has 3 hydrogens below it, right?
Yes. So I guess it would not be symmetrical.
In order for this to be symmetrical, I would have to have 3 hydrogens on the top going in the same direction that these 3 are. Do I have
Copy
that?
that. You do not.
So if I don't have it, is it symmetrical?
No.
Asymmetrical, polar bonds. Is that polar, Blake?
It is polar.
Okay. Dylan, have I bothered you yet?
Nope.
Let's talk about carbon tetrachloride. Does carbon tetrachloride have polar bonds?
I don't think so, but I don't have my electronegativity chart.
Okay, this is a hint, Dylan. There's an arrow here going up. Does it have polar bonds?
Yeah.
Has polar bonds. Now, is it symmetrical?
No.
Got to remember, this is a tetrahedron. Remember what a tetrahedron looked like. Look at that molecule, Dylan.
Yeah, it is symmetrical.
It is symmetrical. Because it's symmetrical, it is not a polar bond. Got a friend, David?
Yeah,
I
I'm
do-
at a bar.
Okay. It's the first time that I have had a liquid class. No problem.
It's a sober bar, so we're drinking a
Do
Cava
not-
Kratom.
Do not tip a beer up, or else I'm gonna have to go get my own. All right, Dylan, did you see that molecule is symmetrical?
Yeah.
I'm going back to where, nope. Where am I at? There I am. The center, guys, are you all seeing that the center one is a symmetrical molecule?
Yes.
If it's a symmetrical molecule, can carbon tetrachloride be polar?
No.
Nope. David, are you kind of getting this?
Yes, I am. I just actually had my lab yesterday, and we did all of these kinds of things.
Okay, good. You just had your lab yesterday?
Yeah.
Wow. You're going to have another one next week?
No, we're off next week, and then I take my final the week after.
Wait, I'm not understanding, because you have another lab, heat of vaporization, you should be doing this week.
You got to go in the back for that.
That
okay?
one is
I allow
what,
you to do such. You can go into.
I think
go in
we've
the
already
back,
done
have
that.
fun.
I thought about it. We went
The
to
heat
the
Okay.
vaporization.
bathroom,
Yeah,
Who
I
do
think
you
that
have-
was the one that we had to do
last
online.
night.
Who do you have for lab?
So maybe we should go in together.
I forget her name, but she's the Polish woman.
Ask her.
Well, yeah,
Ask her
Donna
about
was
it,
telling me.
okay? Seriously. Email her somehow, David, because I think you may be missing a lab. Anyway, not a big deal. Anyway, David, does this have polar bonds?
Which one are we looking at?
Okay,
We're
we
looking
don't
at the
give
bottom
nothing,
right.
or how much?
Yes, it does.
Okay?
If we do like a,
Understand,
Saturday,
carbon and hydrogen
Andy
is a
not
non-polar
part of the
bond,
surgery process because he can't
but the
fucking
carbon
do that.
chlorine is a
So,
polar bond.
Once he's like back
Is
up
this
to
molecule
speed,
going to be polar?
We're probably doing
Yes.
Polar bonds, asymmetrical.
Yeah.
Good deal. How about this one, guys? BF3.
Has polar bonds, but is non-polar.
Definitely down
Why?
to, that's my shit.
There is symmetry between the molecule.
Total symmetrical molecule, therefore it is nonpolar. Are we okay with this, or do I need to get through a couple more examples?
I'm okay with it.
Professor, I have a stupid question.
Who's talking?
Blake,
Okay, hi, Blake.
when you say is it symmetrical, asymmetrical, what plane should we be cutting it at?
Any plane.
Any plane. Okay, so if there's one
Okay.
that fits, okay. Sorry, stupid question.
Literally, no, it's not a stupid question. For example, if you cut the boron along this plane, you see you cut the fluorine in half and both sides of that are the same.
Okay, so you can cut atoms in half for
Yeah,
symmetry.
We're just looking at this to make sure that we're not actually cutting the atoms in half.
Right,
We're just
of course.
looking to see if it's symmetrical.
Copy.
Like this one, is it symmetrical if I slice it this way or this way? They're
Yeah,
both
gotcha.
symmetrical, okay?
Cool,
Whereas
thank you.
something like this is not symmetrical. What happens if I put an H there? Blake, if I replace
It-
the Cl with an H, is
It
the,
wouldn't.
go ahead.
I was gonna say it wouldn't be symmetrical, but I'm thinking it actually would be. No,
Wait.
it wouldn't.
If you have an H there and you chop it among this plane,
Not
right?
symmetrical.
You've got an H on one side and a Cl on the other. It's not symmetrical. All right,
Okay.
are we good with this, guys?
Yep, thank you.
Yep.
All right, let's see where I'm going from here. So guys, in summary, when we're doing this, when we're determining polarity, first thing, you have to draw the Lewis-Strauss structure. You got to predict the electronic geometry around that center atom, then predict the molecular shape. You got to look within the molecule to see if there are polar bonds. If there are polar bonds, then you look to see if the molecule is symmetrical. Knowing all those things, we can determine whether the molecule itself is symmetrical or not. You know, this works out pretty good, hasn't it? Quantum mechanics and all this happy horse shit. It works pretty good, right?
Yeah.
Makes sense.
There are some problems with it. All right. Do you remember what the p orbitals, how the p orbitals were oriented? Do you remember that?
Yes. So P2 would be linear.
No, just how they were oriented. The px, py, and pz. How are they oriented towards each other? How is the x-axis oriented to the y-axis?
Perpendicular.
Or 90 degrees away, right?
Mhm.
So the z-axis is 90 degrees away from the y and the x, and the y is 90 from the x and the z, right?
Mhm.
So if they're all oriented that way, wouldn't the bond angles have to be 90 degrees if the atoms were linking into them?
Yes.
If the bond angles were 90 degrees, then all this Vesper crap can be thrown away. But Vesper works. We know that Vesper works. So therefore, we know that the bond angles predicted by quantum mechanics must be wrong. So we have to come up with another theory. Another thing here. Remember that in order to have a bond, the atom has to contribute an unpaired electron. Blake, how many unpaired electrons does carbon have? There's the orbital diagram according to quantum mechanics. How many unpaired electrons does it have?
2.
So how many things can bond with carbon?
2. Or, yeah.
But we know that methane exists, and that methane's formula is CH4. Quantum mechanics doesn't explain this. The molecule BeF2 exists. I want you guys to draw that. Beryllium has I gotta sit here and look. Beryllium has 2. Beryllium has 2. Never mind. Draw this one, beryllium hydride. Beryllium hydride. Beryllium has 2, hydrogen has 2. So that makes 4 electrons, right? Right? Beryllium hydride exists. BeH2 does exist. 4 electrons. Where do those 4 electrons go?
In the bonds.
In the bonds. So we have beryllium that has only 4 electrons around it. Seems kind of funky. When things don't add up, you change the theory. When Columbus was going out, he worked on the new theory that the earth was not flat. As a matter of fact, Columbus did a little bit of cheating. Come on, David, at least a smile. So, quantum mechanics doesn't work. What we're going to do is we are going to think about hybrids. Okay? We have a tangerine and an orange. Mix them together, we get a tangelo. we have a donkey and we have a horse, mix them together, we get a mule, hybrids. We have a car that runs on gas and electricity. So we got to think about how we can deal with this, with atomic orbitals. So I'm going to change this to the slideshow because that slide's not showing up very well. Where am I at? Yeah, thank you. So what happens is we're going to hybridize an s orbital and a p. When we do that, hybridization, we get a funky looking thing with a small little dumbbell and a big dumbbell. And if we're able to take all four of these together, what happens is the big ends spread out as much as they can and they make a tetrahedron. So if we hybridize one s with 3 different p orbitals, they spread each other out to make a tetrahedron shape. Nothing slide. Yeah. So what happens when a bond occurs is we're getting an overlap of these orbitals. If we get them too far away from one another, we're losing energy. If we get them too close to one another, again, we're losing energy because of the fact that getting them too close together built up the repulsion of the positive-positive. Getting them too far apart from one another makes them not feel each other's force as much as they should. Okay, we can use this overlap of orbitals to explain F2. Each F has a orientation, the orbital diagram that you see below. 1 extra electron. So one of these orbitals only has 1 electron in it. One of the other Fs only has 1 F in it, 1 electron in it. So what happens? Where am I at? Sorry. I
You
lost
went
track of where I'm at. There it is. So if I have these two, one of them has 1 electron in it, the other has another electron in it, quantum mechanics works. But when we have the BeF2, remember, this is beryllium's orbital diagram. Does beryllium have any unpaired electrons?
No.
No.
So therefore, beryllium can't bond with anything. But let's say we promote one of these electrons. We get beryllium around fluorine, and one of these electrons decides to go into the 2p so it can bond with fluorine. So we get a jumping. One of the electrons in the 2s orbital gets popped up to the 2p. But still, I mean, that would explain why BeF2 can exist, right? But we still haven't explained the bond angles. So what's happening is we are getting a hybridization or a mixing of the atomic orbitals that can account for the bond angles. If we mix an S and a P, we get 2 new. Because we start with 2 orbitals, we're going to get 2 hybrid orbitals. And we get those 2 hybrid orbitals, They mix together and make two large balloons that are squeezed in the center. If I mix, yeah, that's the same slide. When I have these two degenerative orbitals, they can align themselves 180 degrees apart from each other, which is consistent with the beryllium fluoride molecule. So what happens is we get this hybridization happening. Now you got to understand energetically, the sp orbitals have less energy than the 2p because it incorporates some of the s properties into it, but it has more energy than the s did. The other thing you have to understand, I haven't used the other two p orbitals on the beryllium, have I? They still are out there. These two p orbitals are still out there. They're just not occupied. What's occupied are my two hybrid orbitals. So we have a series of hybridized orbitals. Each of the hybridized orbitals has an electronic domain and a shape. So basically, in summary, for all of the electron cloud shapes, if I have two electron clouds, that means I've hybridized two orbitals, an s and a p. I'm going to call that hybridized orbital sp. So sp, two electron clouds, sp hybridization, they're 180 degrees apart from one another. If I get three electron clouds, I got to incorporate another orbital. So I'm going to incorporate one s and two p's. So my atomic orbital set is going to be an s and two p's. My hybrid orbital set is going to be three sp2 orbitals. The sp2 orbitals get oriented like a trigonal planar. 4 electron clouds, I have to incorporate an s and 3p orbitals. So I end up with 4 sp3 orbitals, which makes the tetrahedron. 5 orbitals, I have to employ an s, p, p, p. I have to incorporate a d as well. 5 electron clouds, I get 5 sp3d orbitals. They orient themselves in a trigonal bipyramid fashion. 6 things around the center atom, 6 electron clouds, s, p, 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 d, d. So I have 6 sp3 d2 orbitals that look like an octahedron. Guys, this really is not as hard as it seems. All you have to do, count the electron clouds around the center atom. That tells you what the hybridization is. If I have 2 clouds, I need to hybridize 2 orbitals. And it goes in that order: sp, sp2, sp3, sp3d, sp3d2. So if I have 5 orbitals, I've got to include my hybridization, s, p, 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 d. Is this kind of making sense to you all?
Yeah.
Yes, sir.
This is important. When we mix n amount of atomic orbitals, we get n hybrid orbitals. If we mix an s, p, 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 d, d, that's 6 atomic orbitals, then we are going to get 6 hybrid orbitals. The other thing that's important, if you have orbitals that are left alone, like for example, sp3d2, I've used 2 of the d orbitals. Those other 3 d orbitals are still out there. So if I'm dealing with boron, boron has 5 electrons, the 2s is filled, 1 in the 2p. What happens is one of the electrons from the 2s gets promoted to the 2p, and then we hybridize it. So we end up with an sp2 hybrid, 3 sp2 hybrids, and 1 2p orbital. What they do is they work together. They form 3 orbitals, 3 hybrid orbitals that orient themselves in a trigonal planar fashion. For carbon, we promote 1 electron. We then can hybridize the S's and all 3 P's to have an sp3, 4 sp3 orbitals. And they will orient themselves such that we get a tetrahedron geometric shape. Questions about this, guys? Blake, Joe, Min?
No.
We good? Okay. I'm just going through and doing it's just doing the same thing that I've talked about. Basically, to determine the hybridization, draw the Lewis structure, determine the number of electron domains. That's the number of hybrid orbitals you're going to need.
5.
This stuff is just stuff I've gone over. Again, keep in mind we have unhybridized orbitals as well. Blake, NCl3, NCl3, draw the Lewis dot structure real quick.
Okay.
Draw the Lewis dot structure, and I want you to tell me what the hybridization is. Joe, CO2. David, H2O. Dylan, SF4. And Min, XeF4. Done, David? David, hold your fingers up. How many electron clouds do you have? Well, that was a no. Not the right Lewis dot structure. Count the number of clouds around the nitrogen.
So this is what I was a drawing there.
Oh, you're doing H2O?
Yeah.
Sorry, David. Okay, my bad. So there are how many things around the H2O?
4.
So how many hybrid orbitals do I need?
4.
What's the hybridization?
Tetrahedron.
Nope, the hybridization. Which orbitals am I hybridizing?
Oh, the bonds between the hydrogen and the oxygen.
Nope. The atomic orbitals. This is the S and the P's.
Oh, so it would be sp3.
sp3.
Okay.
Joe, do you got it for me? Joseph?
I'll be honest, I wasn't here like past 2 minutes.
Okay.
Which one did you give me? I could do it right now.
I think I gave you CO2. Draw the structure of CO2. The Lewis dot. Blake, do you have an answer
Yes.
for me?
I do.
You have NCl3?
NCl3, yep.
How many things are around the nitrogen?
There's going to be 4.
So what's the hybridization?
sp3.
sp3. Dylan. SF4.
sp3d.
5 things. There are 5 things around the center atom of sulfur. So sp3d. All right, Min, did you get the answer on that yet, Min? Joe, do I have an answer from you?
Yeah, mine's got 4, so that'd be
No,
SP3.
no.
Oh?
Did you put 2 double bonds on either side of the carbon?
Yeah.
All right,
It's 2?
remember, double bonds count as 1 electron cloud.
Okay.
So
That's
you
2
got
then,
how
yeah.
many?
SP. 2, so it's SP.
There we go. I think you guys are getting this fairly good now. And if you want, there's another slide in the program which shows you what the orbitals look like and what the hybridization is. Okay, now we got to go on to another thing. We talked earlier about what makes bonds are the overlap of the orbitals with an electron in there. There are 2 types of bonds that can happen. One is a sigma bond, and a sigma is a direct head-on collision. You have the hybrid orbitals colliding directly into one another. Then you also have the side swipe orbitals, the pi. Pi orbitals are sitting in parallel. If they're sitting in parallel, what happens is above the axis of the bond, electrons intermingle, and below. It's above and below the axis that the electrons intermingle. So if I have a sigma bond, if I get a hydrogen directly hitting another hydrogen, that's along the axis plane of the bond. That's what happens with the sigma bond. It's a head-on overlap. Same thing with hydrogen and chlorine or 2 chlorines. Head-to-head interaction. What happens with the pi bond? Okay, with a pi bond, you have these 2 pi orbitals that are directly parallel with one another. And so we get a side-to-side. It's not a direct, it's a side-to-side interaction. And there's an electron density above the internuclear axis and below it. All single bonds are sigma bonds. If you just have 1 bond in a molecule, it has to be the sigma bond because it's the strongest bond there is. You can't have a pi bond. You see, if you had a pi bond, that would orient 2 of the orbitals to be directly head-on related. So you can't have a pi bond without a sigma bond. If we're involving multiple bonds, the first bond is going to be the sigma bond. All the rest are going to be pi bonds. So if I have a double bond between my 2 carbons here, the first bond is the direct head-on. The second bond that occurs is this pi bonding. In the case of nitrogen, that's a triple bond. First bond, head-on. Second one is a pi bond. Third one is another pi bond. They're just oriented and a little bit different from one from the other. If we have something like formaldehyde, formaldehyde has a double bond between the carbon and that oxygen. So what is happening is we get an overlap between the carbon's orbital and the oxygen's orbital. The oxygen is oriented sp3, the carbon is oriented sp3. Remember, 3 things around the oxygen, right? Right, guys? 3 things around the oxygen, 3 things around the carbon. That means because there's 3 electron clouds, it's sp2 hybridization. And what we do is we get one of those lobes overlapping the other, to have the sigma bond. It's sp2 hybridization, guys. We have a free pi orbital. The oxygen has a has a free p orbital sticking directly above it. The carbon has a free p orbital sticking directly above it. Each one of those has one electron in it. So they overlap above the internuclear axis and below it. If I deal with acetylene is hydrogen, carbon, triple bonded to another carbon, triple bond or to sigma bonded to another hydrogen. How many electron clouds are around this carbon? One carbon, one hydrogen bond. 2. It's sp. This is sp hybridization. Sp hybridization means I have 2 free pi bonds. And if those pi bonds are associated with electrons, I've already brought them close in. I've got pi electrons, I've got p electrons that can interact in a pi bonding fashion. They can go for these 2 lobes and for these 2 lobes. Always, all multiple bonds start with the sigma bond. And it directly tells you what the internuclear axis is. If I'm dealing with this whole molecule, I've got a single bond here. Remember, I said if it's a single bond, it's a sigma. So I have one sigma bond. I've got another sigma bond between this carbon and this hydrogen. One between this carbon and this hydrogen, one between this carbon and this hydrogen. Plus, the first bond of the double bond has to be sigma. So I have 5 sigma bonds, 1 pi. Okay. Let's say I have another carbon out here that's also in an sp2 hybridization. Does that next carbon have a free p orbital?
Yes.
Microsoft fucked over Bungie.
So if that next carbon has a free p orbital, the electrons can get shifted from over here to between these 2 carbons. You have resonance. If you have resonance, that means that literally if you have another carbon out here, the electrons are spread out throughout all 3 carbons, not just over here. It's through all 3 carbons. Okay, if you're able to draw 2 or more Lewis structures in which the arrangement does not change, but the arrangement of the electrons does change, then you have resonance. In other words, if you're able to manipulate the structure so that you have double and or triple bonds that move around, you have resonance. And this is going to be extremely, extremely important for you guys going on to organic chemistry. You need to understand about resonance because it lends more of a stability to the molecules. So I have this. What is the orientation of this nitrogen? What is the hybridization of this nitrogen?
Have a sniper like
SP2.
SP2, that oxygen.
These power ups everywhere because it made the game. And if you
This
didn't like
oxygen?
fast-paced, cool. There was capture the flag.
SP2.
Right, King of the
SP2.
Hill. There was
These two oxygens are tetrahedral.
SWAT because I was
But
really, really
they
good,
have
and that would also make me
2
better
electrons
because-
in its p orbital of these two oxygens. So the double bond can exist here, like as in this structure. It can exist to the right, as in this structure. So you have the electrons being spread out over the entire molecule. That's said to be delocalized. And when it gets delocalized, that means it's a stronger molecule overall. If I have benzene, each one of these carbons is sp2 hybridized. Count them. They all have three things around them. So what happens is they're all sp2 or hybridized. They all have a p orbital sticking above and below the plane, which means that if we have electrons between two of them, that can get shifted to over here, so the double bond can be over here as well, which means that the electrons are going to be delocalized throughout the entire molecule. Another interesting thing, benzene is all in one plane. Benzene is a flat molecule, which is very conducive to adding intermolecular strength that I'll talk about next week. But it's all in one plane because each one of these carbons is trigonal planar. Yeah, I've gone over these things. Pi electrons are the ones that are delocalized. Sigma electrons are already there. They are controlled and in place. Again, all this stuff I've gone over. All right. Couple new phenomena happen. All right. Oxygen is paramagnetic. When we say it's paramagnetic, that means that there are O2 is paramagnetic. If we bonded oxygen with another oxygen, would there be any unpaired electrons?
No.
And then the fighting.
No, because this oxygen's two electrons would bond with this one.
A double
And all
bond.
the electrons would be paired up. Does that make sense?
Yes.
However, we know that oxygen is paramagnetic. That means it gets moved in a magnetic field. In order for it to be paramagnetic, it has to have unpaired electrons. Therefore, this can't exist under atomic orbitals. We must do something else to it. Another thing is, this doesn't really predict double and triple bonds. We have more unexplained phenomena. Guess what? We have another theory. Joe, which one's teaching which one how to use it? Are you teaching the computer or is the computer teaching you?
Great song.
What came first, the chicken or the egg?
There we go. Okay, paramagnetism. It's a property of a molecule which is attracted to a magnetic field. In order for this to occur, you need unpaired electrons. On the other hand, you have a diamagnetic molecule that is not attracted to magnetic fields. There are no electrons unpaired.
As in halogens? Would
I'll get back to
halogens
you on
be?
that. I will get back
Okay.
to you on that, okay? So basically what that means, if you have everything balanced and you put it in a magnetic field, if it is paramagnetic, it's going to be repelled and the weight's going to go up. If it's diamagnetic, it's going to be a slight decrease in the weight there. So in order to explain this, we came up with another theory called the molecular orbital theory. Basically, where we've been dealing with, we've kind of been saying that the orbitals are centered around the individual atoms. What molecular orbital theory does is it says once the atoms get together and form a molecule, we make new orbitals. We make molecular orbitals rather than atomic orbitals. Because even in hybridization, we're still talking about the hybridization about the atom, are we not? So when we're dealing with molecular theory, we're making whole new orbitals, which are the property of the molecule and not the atom. Similar to atomic and hybrid, they have similar shapes and energies. They each can accommodate 2 electrons. You have to follow the filling of the electrons by the Pauli exclusion and Hund's rule. And the number of molecular orbitals equals the number of orbitals combined. So these are the rules we have to live by. Basically, what this comes down to is if we have two atoms and we have 2 s orbitals, they're along the internuclear axis, so they can form a sigma bond. On the other hand, we also have the electrons being located on the opposite end of the place where the molecules are getting close together again. If they're in the opposite end, they're kind of working against the molecule forming. So the ones that are in the right orientation, these are going to be bonding orbitals. The ones in the opposite direction are going to be considered anti-bonding orbitals. If they hit head on, they're going to be called sigma. If they're going to be p, those are going to be pi orbitals. If we're combining an s and a p, that's a sigma. If we're combining 2 p's, that's going to be a pi. So we get, if we're dealing with just the 1s shell, we have 1s orbital from the one atom, a 1s from the other atom. They combine to form a sigma 1s bonding and a sigma 1s antibonding. The sigma 1s bonding has less energy than the 2 regular atomic orbitals. The sigma 1s antibonding has more energy than the 2 atomic orbitals. So that when we mix 2 hydrogen.
I'm sorry, Professor. Did you say that the sigma bonding has less energy?
Sigma bonding, yes.
And the sigma antibond would have more energy.
Look at this. Yes, exactly,
Okay.
David. If you see the slide before you, I have the 1s's on one energy level, right? These 2 1s orbitals combine to make a sigma 1s orbital and a sigma antibonding 1s orbital. The sigma bonding has less energy than the original 2 atomic orbitals. The sigma antibonding has more energy than the 2 atomic orbitals.
Is that something to do with the satisfaction of filling in all of their valence electrons?
Yes. And so, just like Pauli said, Pauli and Hund, if I've got two electrons, one from the first hydrogen atom, one from the second hydrogen atom, they're going to populate the least energetic orbital first. So they're going to both go into the sigma 1s bonding orbital. The sigma antibonding has no electrons. So the rules we have to deal with. The number of atomic orbitals in equals the number of molecular orbitals out. We're going to follow Hund's rule and Pauli's exclusion. In other words, we're going to fill these just like you filled the orbital diagrams in quantum. Bonding only occurs when there's an energy advantage. We can determine when there's an energy advantage by determining what the bond order is. The bond order will determine how stable a molecule is. The bigger the bond order, the more stable the molecule is. So what we're going to do is we are going to add all the electrons in the bonding orbital, and we're going to subtract the number of electrons in the antibonding orbital divided by 2. That will be our bond order. So if I'm doing hydrogen, H2, I have two 1s orbitals. They combine to make a sigma 1s orbital and a sigma antibonding 1s orbital. I have two electrons. They both go in the bonding orbital. So the number of electrons in the bonding orbital is 2 minus, there are none in the antibonding. So I have 2 over 2. My bond order is 1. Remember, bond orders of 1, 2, or 3 are stable molecules. Bond orders of 0 does not have a stable molecule.
Can you repeat that?
Bond orders of 1, 2, or 3. That you're going to have, those are the only choices. You're going to have a 1, 2, or 3 bond order. Sorry, there are 4 choices. I lied. 4 choices. 0, 1, 2, or 3. If you have a bond order of 1, 2, or 3, what that's telling you is you have more bonding orbital electrons than anti-bonding orbital electrons, and the structure is stable. If you have 0 as your bond order, that means the number of electrons in the bonding orbitals equals the number of electrons in the anti-bonding orders, and basically, you might as well have kept them as atomic orbitals because you're not getting any energy advantage. You're getting the energy advantage because the bonding orbitals are slightly lower than the original atomic orbitals. Let's look at helium. Helium, again, 2 1s atomic orbitals. We form a sigma bonding 1s and a sigma anti-bonding 1s. This time I have 4 electrons. So using Pauli and Hahn, first 2 electrons go in the sigma bonding. The next 2 go in the sigma anti-bonding. In the case of helium He2, I have 2 minus 2 over 2. I have 0. What this is telling me is that He2 does not exist. And that is true in effect. Okay, we're dealing right now, we're looking at this chart, and I'm going to put it up on the bigger picture so you can see it a little better. All right. Understand, right now, these are only drawing. They're only drawing the second shell. Because if you notice, this is sigma 2s, sigma antibonding 2s, pi 2p, pi 2py, and 2pz, sigma 2p, pi pi, sigma. We're only dealing with the second shell. You got to understand that really the first shell does exist. The first shell does exist, but all that's going to consist of is a sigma 1s that's filled and a sigma antibonding 1s that's filled. So this is really where we're determining what's happening with things. Okay, lithium. Okay, lithium 2, Li2. All right, each lithium has 6. So an Li2, I'm sorry, excuse me, each lithium has 3. So an Li2 molecule should have 6, correct? All right, the first 4 are in the sigma 1s, bonding and antibonding. So there's only 2 left. So my sigma, my 2s orbital from one lithium and my 2s from the other lithium react to form molecular orbitals of sigma bonding 2s, sigma antibonding 2s. I've got 2 electrons. They go in the lowest energy orbital. So they go into the sigma 2s bonding orbital, molecular orbital. Now, I'm going to do my bond order. I have my sigma 1s that's filled with 2 electrons. I have my sigma 2s bonding that's filled with 2 electrons. So I have 4 bonding electrons. I have my sigma 1s antibonding, so I have 2 antibonding electrons. 4 minus 2 over 2 gives me a bond order of 1. This is telling me that the Li2 does exist. Okay, let's go on to boron. Boron has 4 and 4. It has 8 total electrons. I'm sorry. 1 second. We skipped beryllium. There's a reason we skipped beryllium. Can anybody see why we would have skipped beryllium?
Because it has an odd number of electrons.
Nope. It has 4 and 4, David. It has 4 and 4. So that gives you a total of 8 electrons. If I'm filling Be2, the first 2 go in the sigma bonding 1s, the second 2 go in the sigma antibonding 1s. The 5th and the 6th electron go in the sigma bonding 2s. The 7th and 8th go in the sigma 2s antibonding. I have 4 bonding electrons, 4 antibonding electrons. Can Be2 exist?
No.
4 minus 4 is 0. Be2 can exist. That's why it's not shown here. So, okay, now we're going to boron. Boron has 5 electrons, so B2 should have 10 electrons. The first 4 go into the sigma 1s, as bonding and antibonding. So I have 6 electrons left. 2 go in to the sigma 2s, 2 go in to the sigma antibonding 2s. I have 2 more left. They go into the pi 2px and the pi 2pz. Separate orbitals, guys. The pi orbitals are separate orbitals. So if I'm following Hund's rule and I'm following Pauli's exclusion, each one of these orbitals has to have 1 electron in them. Are these electrons unpaired?
Yes.
If they're unpaired, that's why it is paramagnetic. Okay. Now let's look at carbon. Carbon has 6 and 6. It has 12 total electrons. The first 4 go into sigma 1s bonding, sigma 1s antibonding. So I have a total of 8 left. 2 go into the 2s. 2 go into the sigma antibonding 2s. That leaves me with 4. My pi molecular orbitals are filled completely now. Now, what is the bond order of C2? I've got 2 plus 2 plus 2. I've got 6 bonding electrons. I've got 2 antibonding electrons. 6 minus 2 is 4 divided by 2. My bond order is 2. And something I didn't mention a little earlier. The bond orders correspond with single, double, and triple bonds. If the bond order is 1, you have a single bond. If the bond order is 2, you have a double bond. If it's 3, you have a triple bond. So C2, because its bond order is 2, is a double bonded molecule. B2, on the other hand, has a bond order of 2 plus 2, 4 minus 2 divided by 2. It has a bond order of 1. B2 is a single bonded molecule. I got 2 more of these to go through, and then I'm going to let them slide, all right? I have nitrogen as my next molecule. Nitrogen has 14. Remember, guys, the thing that you got to realize when you're doing this is when you're drawing this out like this, make sure you don't forget the sigma 1s and the sigma antibonding 1s. So the first thing you do if you're seeing the molecular orbitals begin with 2s, the first thing you do is you subtract 4 away from the total electrons, because you have put those 4 into the sigma 1s and the sigma 1s antibonding. So I have nitrogen with 14 originally. 4 of them went into the sigma 1s bonding, sigma 1s antibonding. That leaves me with 10 left. Boom, 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 boom. 2, 4, 6, 8, 10. I have 10 electrons, do I not? All right, 10 electrons. Count the bond order. I have 2, 4, 6, 8 bonding electrons. Only 2 antibonding. 8 minus 2 divided by 2 gives me 3. N2 has a triple bond in it. All right. Now comes the part where I hate molecular orbital theory. We have oxygen. Oxygen has 16 electrons in it. First 4 go to the 1s bonding and the 1s antibonding orbital. That leaves me with 12 left. So if I'm filling oxygen and I'm doing it the same order that nitrogen gets filled in, this would be 2, 4, 6, 8, 10. Sorry, I just got confused there for a second. Stop. Oxygen has 16, 412. Hmm. All right, sorry, there's a real reason. I just completely lost it for a second. I'm sorry, I can't explain this. But you have to realize that there is a break. There's a break between nitrogen and oxygen where the order of the molecular orbitals filling gets changed. Okay, it gets changed.
As in it goes from the p orbital to the p anti-orbital?
Yes. In the end, we fill the pi bonding first, then the sigma bonding. In the oxygen, we fill the sigma first, then the pi. Okay? There's a reason for that, and I'm sorry, it's just slipped my mind for the moment. Stop. I got a dog that's chewing on herself. That stopped her. It was a paper wad. It wasn't hurting her. All right, for right now, guys, I will look into that and I will come up with the reason later on. I'm sorry, I'm at it, and it's at the end of the class period, and I'm sorry, I just can't think.
Professor, I do have a question. So we're kind of doing elements that are further up and have less of the electrons, but when we go further down,
You're not
does this-
going to go further down.
Oh, okay, because I was going to
This
ask, does
is
it go
it.
to like the D as well?
This is it, David.
Okay.
Technically,
These are the only
yes.
elements that would be diatomic.
These are the
basically.
only ones you're going to have to worry about.
Right.
Not the only ones that exist. You have
Okay,
to
got you.
understand, we're futzing with a whole lot of numbers here that we don't have a right to.
Right.
Remember that the Schrodinger equation has only been solved for hydrogen.
Hmm.
So there's a whole lot of things going on here that we're theorizing, but we haven't proven it yet. What I wanted you to realize is there's this line of demarcation. The sigma 2s and the sigma antibonding. That's good. But when we get to the p orbitals, we switch the sigma and the pi bonds. So that in nitrogen, the pi bonds become.
Oh, right. I see what you're saying.
Okay, here's what it is. I just figured it out. I'm sorry it took me that long to figure it out. If we filled the nitrogen like we did the oxygen,
Mm-hmm.
then this orbital, no, that's not right either. Ah, there it is. I'm sorry it's taking me this long, guys.
Okay.
If these were flipped, do you see these two? David may be the only one paying attention to me now. If we flip these two,
Right.
then these two would also have to be flipped. Okay?
Okay.
So that when we went to fill the oxygen, we would be filling this first, and both of them would be in there, and it would be diamagnetic, when actually it's paramagnetic.
Okay.
Bottom line, that dog's going to kill me. Gracie. Okay. Bottom line, guys, when you're doing these orbitals, know that when you go up to nitrogen, they fill sigma 2s, sigma antibonding 2s, pi bonding 2p, pi bonding 2pz, sigma 2p, then antibonding 2px and 2pz, antibonding 2px. Up to nitrogen. It switches. It switches when we get beyond oxygen, where we fill the sigma first, then the pi's, then the pi antibonding and the sigma antibonding.
Okay.
Just
Okay.
know that it switches. And I'm sorry that I
Perfect.
didn't do that in a good fashion. But there is a definite reason why they do that.
Okay.
Any case, guys, that's time. We do not have much more in this. Next time, we are going to be getting into intermolecular forces. We have 2 more chapters. I'm sorry, excuse me. We have 1 more chapter, 2 more lectures. We have a lecture on Tuesday and 1 the following Tuesday. Then we have the test. Now, I sent something into my boss, specifically online classes. Finals are supposed to be given the December 4th through the 6th. I don't know why that is. I may have to adhere to that. So if that's the case, what will happen is I will make the final open from the 4th a.m., 4th is a Friday, 8 a.m. through Sunday the 6th, 5 p.m. If that's the case. If not, what will happen is I will make December 10th the final date.
For the final, with each test you give a practice test, will you give a practice final too?
No,
Okay.
Dylan, that's an absolute no because first of all, the final gets drawn from the individual tests. So in effect, you do have a practical. You have
Okay.
all the other tests are given. Okay?
Okay.
So no, there will not be a final practical. Any other questions, guys?
Nope. Thank you so much,
Mhm.
Professor. Have a great day.
Again, I apologize for that last little fiasco. I will look into it and discover why.
Okay.
All right. Take care,
Sounds
guys.
good.
Have a good one.
See ya.
Have a
See
good
ya.
one,
Have a good
Professor.
weekend. Have a good Thanksgiving. If I don't get to see
Happy
you.
Thanksgiving.
If you
Happy
guys
Thanksgiving.
decide to skip out on me on Tuesday, have a happy Thanksgiving.
Okay.
Alrighty. See ya.